My name is Adwaith Gupta, and I am the founder and CEO of Paanduv Applications. I'm delighted to talk about towards defect-free manufacturing with aluminium, predictive modeling using AM PravaH. I'm very grateful towards the IBAAS team for inviting me for this technical lecture series, and I'm sure I will get to learn a lot from the other lectures that have been presented in the past as part of this series. We are right at the beginning of the monsoon season, and I'm sure many of us are enjoying the delight of mangoes, one of the benefits of living in a country like India. However, an interesting fact that I want to talk about is how this monsoon season causes a dip in aluminium domestic scrap prices and elevates logistic costs, tightening supply side pressures, something to think about when we decide our aluminium businesses down the line. A quick overview about the aluminium market in general, and I'm going to talk about four aspects of this market. The first one is the aluminium powder feedstock, the second one is the aluminium alloy additive manufacturing market, the third one is the powder bed fusion market, and the fourth one is the ALSI 10 mg and other aluminium alloys, how they are optimized and the market around it. If we look at different growth rates, they go all the way from 1.7% all the way up to 30%, but on an average this global aluminium market is growing at a CAGR of 6.23% as predicted for the next 8 years. Additively manufactured aluminium parts are high performance and they offer many interesting mechanical and chemical properties. They have a very high strength to weight ratio and are weather resistant. They are less rigid than compared to steel, and of course there are many other benefits that go around with the aluminium alloys. In fact, we when we travel, when we use cars, there are a lot of components that are made of aluminium alloys already. However, when it comes to the AM printability or the processability of aluminium alloys, it can be quite challenging. But with challenges comes a lot of scope for research and development and further improving the way aluminium alloys are currently used. For example, when it comes to the printability of pure aluminium, it's quite a daunting task. However, when it comes to ALSI 10 mg and other alloys, it could be an excellent option when it comes to laser powder bed fusion type of additive manufacturing. Again, if you try to do multi-material welding, for example, aluminium and copper alloys or aluminium, zinc and magnesium alloys, the printability is again poor. It causes cracking, oxidation, poor weldability and problems like that. However, again, when you talk about aluminium, magnesium, SC and zirconium sort of multi-material welding, then you can again have excellent printability both using direct energy deposition or laser powder bed fusion sort of additive manufacturing processes. When we talk about defects in additive manufacturing, irrespective of whether it's an aluminium alloy or some other alloy, we typically encounter the same sort of defects. They can be more pronounced in the case of aluminium, but the defects remain nevertheless. For example, we can talk about keyholes, which is one of the most scary defects that all 3D printer users want to avoid: spattering, liquid breakup, extreme porosities, whether due to keyhole or even in the other modes of heating, vapor depression, vapor plume ejection, humps that reduce the surface finish of your part, and many other defects that we encounter on regular basis. Talking a little bit more about these defects, specifically for ALSI 10 mg, which is one of the alloys of interest for today's talk. There are many porosity and poor melt pool dynamics related defects. There could be metallurgical pores, there could be keyhole pores, there could be a lot of unmelted powder particles, poor bonding effect, and and you name it, basically every defect that you encounter in additive manufacturing in general, the same sort of the entire gamut of those defects can again be seen when it comes to ALSI 10 mg alloy, which has a lot of applications in aerospace and defense, but it also comes with its own set of defects. There are many ways of getting rid of these defects that we encounter in additive manufacturing industry in general, and the same methodologies are also applicable to the aluminum and its alloys as well. Uh, a typical aspiration for an AM process engineer is to provide a sustainable technology, in this case additive manufacturing, to prevent wastage of material, not only during the experimentation stage but also during the production stage, to achieve a heterogeneous fine grain structure or grain microstructure which directly corresponds to the mechanical strength of your built part, and to produce a near net shaped component requiring a very minimal amount of post processing and finishing to the part. While these are very noble aspirations to have, a significant amount of experimentation goes into eliminating, into attaining these goals. And at the core of it, much of the experimentation that happens goes around understanding the melt pool geometry, goes around understanding the microstructures, using a very fancy machines at times, fancy experimental machines at times. For example, the shape and size of a track relating to build rates, interlayer adhesion, powder layer interaction, powder laser interaction, temperature profile and gradients, and there are many other physics that is indicated. Their interplay is indicated when you start observing the melt pool dynamics using machinery, which unfortunately is expensive but is required. So using these melt pool dynamics data collected from experiments, you can optimize your process parameters. You can utilize, you can employ even machine learning from the collected data, and overall, the AM process engineer or researcher can attain his goals. The challenges in experimentation are of course there. In short, the cost of such experimental machines can be quite huge. The resources that go behind the type of expertise that is needed to operate these machines is quite huge. The cycle time could be in the order of months before you get the data back from the experiments. And then there are material related challenges, process control and reproducibility, human errors, experimental setup constraints, data generation, storage and analysis, defect control and characterization, validation and benchmarking, and iterative nature of additive manufacturing research. I mean, at the rate at which new materials are innovated, at least at that R&D level, at the speed at which the overall additive manufacturing market is processing, there's a very fast iteration that is needed to these sort of experiments. The second approach, which can run hand in hand with the experiments and significantly take off the load from the experimental work and the errors associated with this, is the high fidelity multi-scale simulations, which can eliminate defects from build. So what we see here is a real coupon on the left hand side, and again these are all representative images. They don't necessarily validate each other. The image on the left hand side is a thin plate, a real coupon using 3D printing, printed using 3D printing. Then the second image is that of a high fidelity melt pool dynamic simulation for a 20 layer thin plate build, uh, simulated using AM PravaH. The third one is a microstructure growth simulation, the grain evolution of a thin plate. And the fourth one is the stress and deformations simulations, the data associated with the thermomechanical stress analysis using AM PravaH again. So in short, what I want to highlight is that predictive modeling is quite capable of capturing some of the very hidden details about the defects that can happen in 3D printing processes. It can guide us, point us to the right direction as to what must be changed, what must be optimized in order to produce a very good build, irrespective of the process. So in AM PravaH currently, laser powder bed fusion, wire laser additive manufacturing, and wire arc additive manufacturing processes are captured in great detail. Some of the general capabilities of AM PravaH, of course, include the keyhole estimation, keyhole simulations, gas-induced porosities, multi-layer thermal contours, where you want to understand after how many layers the effect of the current built layer is eliminated on the bottommost layer. So you can see on the plot here that after 9 or 10 layers, the effect has gone away, based on the thermal cycling plot here. Something which is very tricky to do in experiments is laser beam shaping, because there are standard laser machines that exist all over the world. And if you want to make a square laser because you think those lasers are the best in the world, there's simply no way to experiment. The only way left in certain scenarios is through simulations. The last one is spattering again. This is again a very difficult process to capture in experiments given the temperatures, the very high temperatures at which additive manufacturing processes operate. It could be easily 4,000, 3,000 degrees Celsius. There could be very hot vapor plume inside the chamber. So everything that we saw on the previous slide, those defects were captured using melt pool dynamics alone. But then there's a solidification aspect as well associated to additive manufacturing processes. And that's where microstructure evolution, how your grains are orienting, reorienting, or misoriented based on the movement of the laser over a particular alloy, is very critical. You want to look at the crystallographic texture, you want to look at inverse pole graphs. There are, of course, machines, EBSD machines, that can give you these sort of detailed data. But then those machines are very expensive. They cannot be operated on regular basis. They have a very huge cycle time for processing the data. And you can, despite all that, you can do only as much. You can only probably run one or two experiments every month. But with AM PravaH's capability of predicting microstructures using kinetic Monte Carlo models along with other coupled models, these results can be generated in a much easier manner in a very short span of time, and you can save a lot of money on that. In fact, everything that you see on this screen is generated from AM PravaH. Now, it is very important to couple the melt pool dynamics, which is happening at a continuum scale, where all your momentum conservation, your energy conservation, your mass conservation, your phase change, solidification, everything is happening. It is very important to couple that entire gamut of computational fluid dynamics with microstructure data. And to that effect, what we are seeing on the screen on the left hand side is the evolution of a melt pool. You can even see how nicely the vapors are trapped at the hump on top of this bead. And when the same results are projected and solved using the microstructure algorithms available inside AM PravaH, you can see how the grains have evolved over time. So the flow of simulations is, you first run high fidelity melt pool simulations, then using the dynamic thermal and solidification fields, you predict the microstructure evolution. In the background, there's a Monte Carlo nucleation and growth model that is taking care of the grain evolution, grain initiation, and their growth. Again, all these images are mere colorful images. If there's no validation data, real images, real experimental data to validate them against. What we see on the left hand side is a real bead, and what we have in the center of the screen is the EBSD microstructure data from that bead. So the first two images are coming from the experiments, and just look at the third image, which has come from pure simulation from the AM PravaH's microstructure module. Just look at the excellent overlap of these two microstructure images and how nicely qualitatively and quantitatively the microstructure data information is captured using the microstructure algorithms. What we are trying to what I'm trying to say is that AM PravaH is world's first all-inclusive simulation software for AM industry. We understand why it is for AM industry because it caters to different processes within the AM industry. But more importantly, it is all-inclusive because we are going all the way from the powder manufacturing using gas atomizers, plasma atomizers, water atomizers to powder spreading to melt pool dynamics to microstructure grain evolution and finally to the part scale deformations and stress information. And to my understanding, if you can capture all these five aspects of an additive manufacturing process, you have basically attempted at the best optimal defect free part production. So we do end-to-end simulation for AM PravaH for additive manufacturing using AM powder to part scale. AM PravaH cuts down the cost by 67% in initial process optimizations, 20 to 30% savings on material costing, and it can reduce the rate of failure by approximately 10%. It saves experimental trials and characterization, and sometimes it's not about saving the number of trials, it's about doing the right type of experimental trials. You don't want to take a very diverse set of experiments just to figure out something close to optimum. You can attain close to optimum solution using simulations, and then around that optima you can do more experimental trials. And clearly for AM processes and including LPBF, this could emerge as a very good virtual twin as well. Today, for the purpose of this talk, because uh, there's a huge audience, I presume, which will be very interested to know about the simulations of uh, additive manufacturing processes. It could be LPBF or just a good old welding process for different alloy of aluminium, or it could be pure aluminium, or it could be aluminium and copper welding. So in the first case we'll be looking at pure aluminium. In the second case we'll be looking at ALSI 10 mg alloy, and in the third case we'll be looking at multi-material weld of aluminium and copper, and we'll see how these simulations give us different insights about these processes and how well they compare against the experiments. Case 1 is the 3D printing of aluminium plate using AM PravaH, high energy density, and there's a huge interplay of multi-physics. I would like to bring your focus to the genuine high fidelity nature of these simulations. Just look at the image on the left hand side, which is coming from the experiments, and the image which is coming on the right hand side, which is coming from AM PravaH. Notice the defect formation, the pore formation, the hump formation, and you name it. While this simulation may look quite straightforward, but the amount of physics equations that are solved in order to capture this process accurately has been quite challenging. I want to play another video from a different angle and at an even higher fidelity. Just look at the pore formation, how some of the pores are stuck in the solidification phase, some of them get ejected out. Even observe the plume, the vapor plume. I will play this one more time. Just observe the vapor plume which is coming out from the melt pool. And this is one of the rarest solvers in the entire world which captures the vapor plume in its full glory. Most of the solvers that we have either have the uh, solid alloy phase, they have the molten phase, and that's it. But in our case, we have the solid alloy phase, the molten alloy phase, the metal vapor phase, and the fourth phase, which is shielding gas. And all these four phases are captured and simulated in completeness so that we get the most accurate results. Now let's look at some of the experimental comparisons. So we are looking at the front wall of the weld of the melt pool in this case, which is quite important in understanding the defects and how well the overall surface finish of your build part would be. So the front wall experimental angles were reported to be 85 degrees. See, of 5 degrees short of 90 degrees. And what we are seeing at different times from the simulation, at 80 microsecond we are seeing 85 degrees, at 180 microsecond we are seeing 82 degrees, and 260 microsecond we are seeing 81 degrees. Average keyhole depth is 200 microns, and we are also observing very similar depths in our simulations as well, around 200 microns as well. So very nicely matching the experimental data despite all the complicated physics that goes behind it. Again, I want to highlight on the pore formation. I mean, that is something, and the hump formation. So all the mass which has ejected out from the melt pool has got been deposited over the top, as you can see on the experimental image on the right hand side in the big oval, and then on the left hand side again you can see a lot of deposition of material behind the melt pool. Similarly, the pores are almost spherical in nature, as we can see in the experiment and in the simulation. The pores are not only spherical, they are almost at the same location. So if you observe at this particular circle, and if you observe at this particular circle, they are quite identical. Then you have another pore here, you have another pore here, this pore is probably this one, and then even a pore is formed here, which you can see a slight hole. You can see a slight hole right here. uh, the analysis is incomplete if we don't comment or talk about microstructure grain growth. I won't be comparing this against experimental data here due to the lack of that sort of data, but you can see how nicely and how in a great fidelity the microstructure information is also captured for this pure aluminum plate uh, laser interaction. And you can see equiax grains, you can see columnar grains, and such. In case 2, I'll be talking about ALSI 10 mg plate using AM PravaH. So let's play the video first. Again, I want you to appreciate the particle dynamics aspect of it as well. You see how nicely the particle bed is prepared over the alloy substrate using discrete element modeling without any approximations at all. And you see how nicely the melt pool is progressing as the laser progresses over. There's of course an aspect of vapor which is hidden for better post processing here, and you can see how the bands are formed, as is the case in real 3D printing uh, melt pools. uh, ALSI 10 mg is a huge thing in additive manufacturing because of its high printability. It has a balanced mechanical and thermal properties set, lightweight design potential, compatibility with post processing, strong industry track record, thermal and corrosion resistance, and microstructure tailoring. I mean, so you name it, pretty much everything that you desire from an alloy is done using ALSI 10 mg. No wonder it's of interest to the users. We have done a couple of variations, compared it with experimental data for different power and scan speed and spot diameter variations, and the width and the depth that is reported in simulations matches quite well with the experimental width and depth. Again, melt pool depth and width are the first step in identifying the mode of heat transfer, whether it is keyhole dominant or conduction dominant, convection dominant, radiation dominant, and accordingly, much of the defects that are formed can be understood. So the deviation when it comes to depth is 5 to 20%, or in the second case it's under 1%, and deviation in depth is 3 to 39%. So again, we are talking about errors typically in the range of maybe single digit percentage errors, all the way to up to maybe if you take an average of the second one, perhaps 15 to 20% error. Again, without commenting on the pores amount, these pores could be formed of the trapped vapor. They can be formed because of the trapped shielding gas also. So again, I mean, a lot of commentary on the pores is quite important in understanding the overall structural integrity of the melt pools. Moving on to the microstructure defects, or I'm calling it structural defects, because microstructure information can give you, microstructure data can give you very good information very good pointers towards how well uh, this particular build part is going to behave when it comes to the mechanical properties, mechanical strength of the build. You can see a lot of, again, lot of equax grains are formed, lot of columnar grains are formed towards the edges, towards the solidification face of the melt pool. However, as we move right towards the center, you can see the circle here, more of equax grains are formed. And this is, and what you see in the center two images, so the leftmost image is coming from AM PravaH, the second image is experiment, the third image is experiment, and again the fourth image is again coming from AM PravaH. So you can see how nicely, if you look at the arrows, the equax grains are matching quite well in the first two images, and again equax and columnar grains are matching quite well across the cross section in the last two images. You can estimate the structural property using many empirical formulae, or you can further do other sorts of analysis. I mean, that is in the hands of the material scientists or the mechanical engineers, how you really want to use this microstructure data. But in the past, this microstructure data has been used with a strength mechanism, Hall patch equation, to predict the yield stress of your build part. And in order to do that, the AM PravaH software not only gives you images, but it also takes the entire 3D grain information, gives you the mean and the standard deviation and higher moments as well for that data, so that you can use this mean grain size into Hall patch equation or other equations of your interest and predict the yield stress, hardness, corrosion resistance, and other sorts of other sorts of mechanical properties of a build part. The third case that I want to talk about is aluminium copper multi-material welding, a relatively a new development in our team. Just want you to appreciate that here the number of phases is quite huge. There's a copper solid phase, there's a copper melt phase, there's an aluminium solid phase, there's an aluminium copper phase, and then a laser is being shot down, first penetrating the aluminium phase and then penetrating the copper phase. And look at the fusion of this interface, how nicely copper is fusing into aluminium, solidifying, and a little hump is formed. If you look at the right image, also called a weld crater. These scenarios come up quite a lot when you talk about battery systems, where we want to join copper and aluminium in battery tabs, aluminium carbon fiber composites in electric vehicles and aerospace, metal ceramic interfaces for implants in biomedical, and of course in additive manufacturing. There's a lot of R&D that is happening in multi-material 3D printed parts required for integrating joining strategies. Right. Now, one chunk that we haven't talked about, which is right at the beginning of this entire simulation cycle, which is the powder production. When you talk about melting a part using a laser, there's always some form in which that metal comes in. It could be a wire or it could be particles. In most cases, it is either wire or the particles. A wire, while it may be a simpler process, the powder production in itself is a quite challenging process, and there's limited number of atomizers that are available to do that. Now, if you don't want to atomize, produce your powder particles using atomizer, where you have either very high speed guns of water, gas, or plasma hitting a chunk of your metal and atomizing it, that is one way to go through. The second option, which is ball milling, the good old ball milling, but in that case, the sphericity of your powder particles is quite bad, and hence the amount of defects that you can see during 3D printing can be quite huge. So you can see on the image on the top left here that water atomization gives you the worst sphericity, followed by gas atomization, and then plasma atomization really gives you very high grade spherical powder particles. If you have a limitation of an atomizer, then such simulation software become even more important, because then, despite having a poor quality of powder, you still want to have a very good quality of the build. and the only option you have is to play around with the process parameters, adjust your laser powers, adjust your uh, inert gas, your chamber conditions, adjust your scanning strategies, your scanning speeds, which is all in your hands. And despite having a poor powder grade, you can still end up having a very good part. And for that, you require a good amount of optimization, and AM PravaH can come very handy in such scenarios. Now, that is one way where you can simulate, you can somehow work with poor powders. But another application of AM PravaH is direct atomization simulations as well, because even if you have an atomizer, gas atomizer or plasma or water atomizer, it is quite tricky to adjust its process parameters so that you get the desired sphericity. And to that effect, we have also done some work on supersonic inert gas atomizers, where you have a small metal, molten metal, solid metal block in the center, and you have Mach speed 4 up to Mach speed 4.5. In fact, at that speed, your inert gases is impinged onto this metal block, and that atomizes the particles. And if you see, look at the bottom plot, you can see the powder size distribution that you have obtained after this atomization process. You can imagine the physics and the coupling of the physics in particular is quite extreme here. You have gas liquid interaction, which is multi-phase flows. We are talking about primary breakup, where molten jet is disrupted by high velocity gas jets. We're talking about secondary breakup, where large ligaments or droplets disintegrate into smaller droplets. You have compressible gas dynamics. We are talking about high Mach number flows, so you have to use compressible form of momentum equations. You have surface tension and capillary instabilities. You have temperature dependent surface tension, because temperatures can go quite high in this. It could be instabilities. You have thermal effects, of course, heat transfer, interaction of hot metal with cool inert gas, includes radiation, convection, conduction. And then at the very end, as your atomization has happened, these powder parcels travel down under the influence of gravity and solidify midair. And this is where your fragmentation, droplets, rapid cooling of the droplets, all these things become quite important, and probably microstructures also become important as we uh, try to simulate powder manufacturing. All in all, with the invention of AM PravaH, we are trying to upgrade every company's technology to its cutting edge, especially in the field of aluminium industry, by making high fidelity physics-based computational engineering an integral part of their workflow. We have been very fortunate to be associated with some of the top innovators, research labs, engineering companies all over the globe, to have provided their data, to have worked with us, trusted us in providing solutions which are typically quite complicated and cannot be dealt with existing commercial softwares. So very thank you. A lot of thanks to these companies and the collaborators. We are located in Bareilly, Uttar Pradesh, at our Paanduv applications head office, and thank you very much for your time and attention.